Okay, we are, it's 11:44 according to that. And this session is supposed to be at 11:45, but so we get started. And thank you very much for being here. It's right lunchtime. So I guess you're very hungry for knowledge. So that's why you're here. So, and unfortunately, this is scheduled in a very odd time. So, but this is an important and critical issue in Virginia and all over the place. Okay, basically we are talking about coastal. So I'm the moderator. I forgot to introduce myself, but I'm the moderator, and also I'm an advisory committee of the Environment Virginia. And so we cut the introduction short when Scott comes here and Molly, so you can introduce yourself as long as you want. Okay, so. Okay, in Virginia, and cannot see it, 40% of Virginia population lives in Eastern Virginia. And that's a lot, several million people. And actually, if you move upward from there toward DC area, close to 60% of population in Virginia live in coastal environments. And that's the environment which is about 100 kilometers from the coast to inland. So there's a lot of people. So based on that, so there's a lot of pressure on not only water resources demand, but also on water resources pollution and everything else. In the US, about 50% population use in coastal areas. So Virginia is on the high side, actually. But today our talk is mostly relates to Hampton Roads area, which are a number of localities by the Chesapeake Bay. We have big cities, Virginia Beach, Norfolk, and Newport News among the cities. So we are talking about focusing on that area. So in the coastal Virginia, the problems are public water supplies, significant increase, and also projection by 2030 as the population grows. So we depend on freshwater resources, surface and groundwater. And then domestic water supplies, groundwater, which Scott will talk a lot about it. And crop and animal production, we need fresh water for that. Industrial uses and thermoelectric, we got a lot of power plants in the area too. So there's a lot of pressure for water demand in the area. So I like my slide, this one. This picture is of Virginia Beach that you see. But on the right side, this shows the interaction between salt water and fresh water. And basically, when we draw a lot of fresh water, the water level goes down, and the pressure balance is changing. The salt water is coming in. So the coastal Virginia has got a lot of brackish water right now, which is being used actually, which is will be talked about in a few minutes. So water problems, high water demand due to increasing population, groundwater decline, withdrawal, of course there's water management that will be talked about. Low natural infiltration due to urbanization. All those cities that you see, we urbanize. It means a lot of pavements, so we don't infiltrate any natural water there. Everything runs off. We don't get it to groundwater. And then saltwater intrusion in the coastal aquifers that I just mentioned because of groundwater table decline. And also sea level rise. When sea level rises in the coastal areas, it changes the balance of pressure between sea level and fresh water, so the water comes in. And climate change and consequences. So extreme weather patterns and sea level rising, and flooding. So these are the topics which will be covered today. So we have 3 people talking, and our first speaker is Scott Kudlas with the Virginia Department of Environmental Quality. He will introduce himself, and then Molly from VIMS, Molly Mitchell. And then I'll talk at the end, the third speaker. So, and these are the topics of our talks for this morning, and I hope you enjoyed. So Scott, did you load your slide? Did you load it? Okay, so,
They should be on the desktop.
okay, so let's see, I minimize this.
It is on. I was wondering why he was using that.
See, I can minimize. I have to minimize this thing.
There.
But it doesn't. This mouse is the mouse here. Okay, let's find yours a while. This is strange, it's not working. Okay, is there a technician there, somebody? Never checked it. I mean, why this doesn't work? Why didn't you introduce yourselves?
Okay.
Is the technician here? Somebody? Somebody in the room?
Well, I guess I'll introduce myself. I'm Scott Cudless. I manage the Office of Water Supply at DEQ, and what that means is I oversee the surface and groundwater withdrawal permitting programs, as well as a handful of other things, including the state comprehensive water supply planning program, some groundwater and flow monitoring, and then drought assessment and response. So that's kind of the universe that I work in, and as a result of those efforts, I probably have run into you on occasion, many of the people out there, all 20 of you, I think.
This mouse is not working, cannot minimize this thing, so to get to the desktop.
I don't know. Okay. You're not going to have any time when we get done. You might be techier than we are.
This mouse is not working, so cannot close it or cannot minimize it to get to the next slide.
Can you use this?
No, it can work. I mean, we can show the slide, but I want to close
We need to
this
go to
one
the next one,
to
next
go to the next
presentation.
slide, next presentation. So,
Yeah, there was a,
and there's no mouse. There's no other mouse here.
I see. Weird. I see it wanting to do something. Yeah,
Maybe
there, because I actually
click up a mouse
Yeah,
on it?
yeah. That's great. I thought we had one up here.
Well, this is,
I didn't know.
I don't know if this has the right
Hey, there
driver,
you
but
go.
okay, there you go.
Okay, perfect. See,
Where was this
Hey,
mouse?
it
you guys
occurred
are
to
better
me.
than me.
Where was the mouse? Where did you find it?
In my bag,
Oh, in your
from my
That would've been
computer.
his mouse. So Justin didn't leave a mouse up here.
Okay, Environment Virginia needs Scott with his mouse.
Sorry about that.
It's okay.
Sorry, I'm glad you figured it out.
Thank you.
for having me.
No worries.
Okay.
The winner and still Tammin. I guess it's still morning. Good morning, everybody. I want to thank Tammin for inviting me to participate in today's panel. So in the interest of time, let's get started. I'm going to be talking about DEQ and stakeholder efforts to manage groundwater supply in Virginia's coastal plain, which is the area circled here in red. I know this is review for some of you, but bear with me. DEQ regulates groundwater withdrawals within the eastern Virginia groundwater management area, shown here in green, and the eastern shore groundwater management area, shown in the kind of tan color. Since the mid-1950s, these are the three primary issues that we've been trying to manage in some form through our various statutory and regulatory programs: declining head, reversal of flow, and land subsidence. These are 2015 groundwater hydrographs. While as managers of groundwater resource, we expect to see head declines due to use. However, by around 2010, our monitoring wells throughout the coastal plain had been showing consistent levels of decline, even after managing withdrawals under the current regulatory framework for over 20 years. So that caused us some significant concern. And then that information really was kind of corroborated by our modeling work. So based on the permits that we had issued at that time, our modeling tools were also showing a significant risk of aquifer dewatering over the next 50 years. On this particular slide, that's the area shown in red. That's, most of a multi-county area, 3 counties. So, that really generated some concern for us and urged us to take some steps to try to address that. The combined monitoring and modeling information was, as I indicated, a source of significant concern, and we had to move forward to address that. It became clear fairly quickly that we needed to not only halt head declines through reducing permitted withdrawals, but also to plan for increasing water supply through alternative sources to allow for future economic growth over the long term. This would be our best opportunity to put the aquifer system on a more sustainable path. That's not what I wanted. Sorry about that. So have you ever tried to take something away from someone that you previously gave it to? I want to tell you, it's not the easiest thing to do. People kind of get accustomed to having it, and they don't really want to give it back. So, it's a bit like trying to turn this 90,000 tons of diplomacy around. And this is kind of what you end up like if you're a regulator. You can easily look like this. There were days I felt like that, but by and large, they were pretty good to me. So what did we do that allowed us to work on a successful, in our view, successful 7-year process that crossed 2 gubernatorial administrations? We did a number of things. We had a strong foundation in data-driven decision-making, and I think that was very, very important to how that process went forward. We had a very intensive collaboration with our stakeholders, including an important multi-year advisory committee that the General Assembly set up for us. We didn't ignore the economics. We commissioned Virginia Tech to do an economic study that was very useful, I think, for illuminating some of the trade-offs that we wanted people to consider. We tried to be as transparent as possible as we could be with all of the various stakeholders and the folks that we were asking to give up some things. We tried to be extremely flexible in how we looked at taking those things back and tried to hear the concerns of the stakeholders to do that. And I think all of those things collectively and by briefing the legislature early and often help build the legislative support to allow us the time to work through those issues with our stakeholders. So, after several years of tough negotiations and a lot of effort by numerous smart people, we were able to take the first significant step toward long-term sustainability. We did manage to reduce overall permitted withdrawals by approximately 50%. We see that as a very significant accomplishment. And this first map here is the reported use simulation from last year. And you can see, compared to that previous slide that I showed you, that the area has gotten significantly smaller, and there's a lot less red. And the red that you do see there, which represents dewatering, is areas that are so thin they, in effect, started as dewatered at the beginning of the model simulation. So they're probably not restorable. And then this is the counterpart to the slide that I showed you earlier, which is the 2018 total permitted simulation. And again, there's very few red cells there, and the tan cells that represent noncompliance with the regulatory water level are significantly reduced as well. So we made a step forward toward greater sustainability. Water level decline should stabilize or improve by 2030 if our modeling is in the ballpark, without, unfortunately, major new withdrawals coming into the system. And what that really does for us is that provides us time for folks to develop alternative sources of supply, and for those sources of supply to come online and get integrated with our stakeholders' facilities. It also provides time for key conversations and management policy discussions to occur, so that if significant changes are needed at the regulatory or statutory level, we have time to do them without significant pressure driving us so that we don't make mistakes, perhaps. And it provides, let's see, I keep trying to go to the wrong thing here. I am sorry, guys. Increases in supply include new or expanded surface water supplies. We have seen some significant activity in that area since we started this effort. We have seen and issued permits for surface water supplies for James City County and for New Kent County, which are going to significantly increase the availability of surface water in the York-James Peninsula. And the Western Tidewater Water Authority has recently exercised a condition in their permit that allows them over the short term to withdraw a little more groundwater while they expand their surface water storage. So we're very excited about all those steps that have been taken by our stakeholders and think that they're going to be very valuable in the long term. And then, of course, the big gorilla in the room that lots of people are excited about and many people want to talk about, and you can get all the details on that project tomorrow morning, the SWIFT project. Their goal is to help recharge the aquifer by injecting as much as 100 million gallons a day into the aquifer system. So we're very excited about the potential that that project brings, and hope that it is successful. But I think there are some caveats and some cautions that we need to make. First, while we've taken significant steps toward improving the aquifer condition, it's still not in compliance with our current regulatory framework. We still have simulated critical cells that are below the 80% drawdown criteria that we use as a measuring stick. And we still have a few of those red cells, so we still have work to do, and we will continue to do that. The other thing is that we had some legislation that passed back in 2015 that allowed us to keep track of some of the unregulated use out there, which is primarily individual private wells. And so when a new well is drilled in the coastal plain, that well driller has to provide information to DEQ. And we've seen about, over the last 3.5 years, about 6,000 new wells drilled within the management area. And so given those kinds of annual numbers, our concern is that over the next decade or decade and a half, if something's not done about that sector of the water use, we could outstrip the gains that we just achieved through those permit reductions. So that's something that we need to do. The other thing is that all of the changes that we made don't in and of themselves actually produce any additional supply for increased groundwater withdrawal. There is some available supply in some localized areas, but it is still fundamentally a cap system in many ways. And then finally, again, if the modeling is in the ballpark, we don't expect to see significant regional benefit from the SWIFT project for approximately 7 to 10 years. So we're going to have to tread lightly until we can verify that the SWIFT project can work the way that we expect. But as I said before, we're still very supportive of that project and hopeful that it will do what everybody intends. So going forward, how are we going to try to manage some of these challenges for the future? We're kind of relying on what I call the 3 legs of our integrated management framework. We have our water withdrawal permitting program, we have our monitoring and ongoing research, and we do have water resources and water supply planning that's an ongoing activity at DEQ, and we think that that puts us in a position to do very well to address the problems that may come up in the future. So what are some of those future challenges? Well, I mentioned what do we do about the growth in unmanaged withdrawals. Inundation of areas with existing wells provides a conduit for saltwater to enter the aquifer and speed up the process of saltwater intrusion. And again, there's just some uncertainty with SWIFT. I guess what Tammin didn't reiterate, but we're going to hold questions toward the end, and hopefully we will have some. There you go. Is it this one?
Yeah, I think that's the one probably.
That's it, yeah.
Yeah.
Okay. I clicked it twice. There you go.
All right, thank you.
Yep.
I'm Molly Mitchell. I'm from the Center for Coastal Resource Management at the Virginia Institute of Marine Science. And I'm talking today about sea level rise and adaptation and how we're dealing with this issue, or how we'd like to deal with this issue in some cases, in the eastern part of Virginia. So my research is kind of broad, but I focus on understanding the actual risks and the projections and what we're expecting to see and how that will impact our communities, and then what types of solutions are available, and then trying to communicate that information to the people who ultimately make the decisions. Okay, so before I start talking about sea level rise, I want to just take a minute to appreciate again the distribution of population around Virginia. These are our 3 big population centers. They are all on the water. But the other important thing about them is not just that there's a lot of people who live there. These really are the economic centers of Virginia. So when they have flooding problems, we have an economic problem, not just a personal problem with floods. The other thing I want to point out before we move on is that these areas are very different from these areas in some respects, because the more rural areas are a lot of private wells, and there are a lot of septic systems. And so although I'm not really going to talk about those issues much, just keep that in mind that when we talk about the problems involved with sea level rise, they're a little different between the 2 areas. Okay, so flooding is a major problem for Virginia. And why is that? Well, sea level's coming up, but the other problem is we have this extremely flat coastline. So we have these terraced landscape that steps down to the water, And the Suffolk Scarp is from the last high stand of sea level. And everything below that is really less than about 10 feet in elevation. So it doesn't take a ton of water to make big impacts in this region. And a good place to see that is in Norfolk. In the Ghent area, the hours of inundation have increased 577% since the beginning of the century. So that's a lot more flooding that we're experiencing now. Okay, so what are we expecting to see? So we know that there is a lot more flooding coming in. And so this map is showing vulnerable areas, and it's a combination of areas with land below 10 feet, but also high wave energy and exposure, and a little bit of population in there. But mostly I want to focus on these graphs over here. So this is Annapolis, so up at the top of the bay, and this is Norfolk, so down at the bottom of the bay. But the projections for both sites are essentially consistent, that we're looking at about a half meter, so 1.5 feet of sea level rise by 2050. And these two bars here, okay, encompass this. This is the kind of annual variability you see in sea level. So the orange line is the mean sea level, which is what we're usually talking about when we talk about sea level rise. We talk about the mean sea level, but you can see in any given year, sea level actually fluctuates around that mean. We expect that fluctuation to continue. So if we take that out, it's 0.67 meters. It's a little bit higher. It's like 1.75 feet to 2 feet is really what we want to be planning for things that cannot get wet. And then I just want to bring, the stuff I'm showing you is based on tide gauge data. But I wanted to bring in these purple lines here are NOAA's models, so these are climate models. And I want to point out that although the tide gauge data is suggesting that right now we're headed for this kind of intermediate 1.3, 1.5 feet in 2050, the 3.3 feet is not out of the question. Okay, so if ice sheets melted much more rapidly than they have been in the past, we could be looking at a great deal more sea level rise. This does make planning a little difficult because we don't know exactly what our endpoint is. Okay, so how does flooding affect us? It affects us in two kind of different ways. So storm surge is the one we always think about. It's when these big storms come in and we get huge floods and lots of people's homes get destroyed. And these are very expensive events, but they're relatively low frequency. Now the nuisance flooding is becoming a bigger and bigger concern. So these are, road closed for a couple of hours. These are typically high tide events, maybe winds pushing water up. They're not the big storms though. And these are happening, not only do they happen frequently, they're happening more and more frequently over time. And so the cost per event is small, but those costs start to add up. And they recently did a study in Annapolis looking at the loss to stores from flooded parking lots. And they actually found a substantial economic impact from just a few hours of flooding periodically. Okay, so now I'm going to talk about some of the issues that we expect to see, and we are seeing. And I'm going to talk about some of the solutions also that are being looked at. In the transportation world, I'm not going to talk about the solutions, but there are some people from the VDOT's transportation research group who are giving a talk tomorrow. So you can go hear what they have to say. So this map shows road closures due to flooding. And each dot represents a single road closure. And the size of the dot represents how frequently it had been closed between 2008 and 2012. And so what you can see is we have some certain areas where the frequency is quite high of the road closures. So that is currently. So with sea level rise, if we look at it, we expect to see in Virginia about 1,500 miles of road actually going underwater. So that's road disappearing. And then the road closures, the other areas, are going to become flooding more and more frequently. So this is a really big issue that the state is trying to grapple with now, and the cities and localities are trying to grapple with. There have been a couple areas where they've raised roads. That's a really expensive project, and it's probably not going to happen on a systemic basis. There's also been a lot of new signage that's been put in. Okay, one of our other big problems is reduced capacity of stormwater systems. And we have normally our rainfall comes down, it goes into a stormwater system, and then it outlets into the water, the river, the bay, wherever you are. But what happens with sea level rise is the water, these outlets are frequently right above high water. And as sea level has been rising, even a high tide can sometimes start to back up into the pipe. So now when our rainstorm comes, our pipe, which was sized for a 10-year storm, already has part of its area taken up. And so now maybe it can only handle a 5-year storm. So what we get is we get inland flooding that's freshwater. It's not actually saltwater, but it is a serious problem. And it's happening in houses that aren't on the waterfront. So sometimes they don't have flood insurance. They're not actually expecting to get flooded. The other thing that's happening down in the Norfolk area is sometimes on high tides, these will back completely up and there'll be saltwater and fish in the street. Okay, so what do we do about this? So the big real solution is that we need to manage our stormwater on the land before we take it out to the water. This is an example from New York City where they have this blue belt, and the idea is it's a series of natural systems that feed into one another and hold stormwater, precipitation water, until it has an opportunity to pump it into the river or to drain it naturally. In a lot of urban areas, they also do this with holding tanks and that kind of thing. They don't always look as pretty as this. But the most common solution we've been using right now has been putting these tide flaps on the ends of pipes. So this solves the problem of getting the salt water into the pipe. It keeps the capacity bigger, but of course the pipe can't drain unless the water is low enough for the flaps to open. But this is the fix, the current fix, and then we need to figure out a better way to manage our stormwater overall. So we expect to see storm surge and coastal flooding increase as the shoreline moves inward. A 6-foot storm surge now moves further inward than it used to. So we expect to see flooding in areas that aren't flooding at this time. So what are we doing about that? Well, most of the solutions are actually on the individual property owners. Most of what we're doing about this is raising houses. And although there is some cost sharing involved in raising houses, a lot of that falls onto the individual property owner. So what we get is we get not an entire area being raised. We get a house here being raised and a house over there being raised and a house here. So that doesn't lead to community resilience. It's just an individual resilience. There are a couple of other techniques out there, and this is one called floodable infrastructure, where it's actually a waterproofed building. So the water comes up on the outside, but it doesn't get wet inside. And there's floatable architecture. But these are still individual property solutions. The more efficient way to protect things is to use a big structure. The one we're most familiar with in the United States is levees. Levees are not a great option for the Chesapeake Bay, though, because if you take a look, you see we have all these rivers, all these edges, right? You would need so many miles of levee to protect an area. In addition to which, this area is almost always privately owned along the waterfront. So that's another thing to negotiate with people. So the big interest has been in this idea of storm surge barriers, which go across the mouths of rivers. So for example, you could put one right here across this area. And then that prevents the storm surge from moving up into the river and protects everyone inside the basin with a single structure. And because there's a lot of interest in this and a couple of them have been proposed, I just want to spend a minute talking about the costs and the benefits of this. So the advantage is that for a relatively small structure, you get a high degree of protection. You protect a large area. And you still allow ship access, you still have your estuarine flushing, that kind of thing. However, there are a lot of potential drawbacks. Anything you do that stops a storm surge from moving up a river will also stop the precipitation from moving down the river. So it does lead to increases in freshwater flooding sometimes. It can trap pollution and sewage, disrupt the ecology of the system. But there are two really big ones to me. One is that as soon as we put this structure in, we assume all this area above it is safe, and then we go and build in it. And this is what's happened on the Thames River. So now there's building in these floodplains. If this structure fails or is overtopped, there's a huge potential for catastrophe. And then cost is the other one. So if you look at the scale of the boat, okay, this is not a terribly big structure. but this was a $14.5 million project. And these are some other storm surge barriers from around the world, and these are their costs to install them. And there's also maintenance cost that's about 10%, 5 to 10% of that initial outlay, and that's in millions of dollars. So these are not cheap projects. You really want to target what areas you want to protect when you're going to use one. Okay, and then the last problem I just want to introduce, but I'm not going to get into the solutions because that's what Tammin's going to talk about, is the saltwater intrusion. And it's not only getting into our drinking water, it's getting into our agricultural fields, and that salt ruins the agricultural fields. This is a big problem for those private wells, okay, but again, that's a personal problem. So those people who own the wells have to re-drill new wells, that kind of thing. It's also a problem, this is the Chickahominy River Reservoir. This is a Newport News reservoir. And this is mostly a freshwater river, but periodically it gets salinity in it and it can wash up over into the reservoir, and then it can't be used. And that's something that's going to become an increasing problem down the road. So then the water will have to be additionally treated, or they'll have to find another source of water. Okay, and so the last thing I just wanted to leave you with was this trying to communicate out to stakeholders and things. We have, in collaboration with some other NGOs and educational institutions, put together an adaptva.org website. And this has all the data that we can provide that is accessible across the coastal plain. And it also has, so it has the forecasts, it has adaptations, and so what are some ideas for how you can plan? And then it also has this planning policy section. And so this is really, big adaptations are going to go in some places, but adaptations that are based on policy is where probably most of our adaptation is going to occur. And so this talks about zoning changes and that kind of thing. And we're going to hold our questions till the end, but if you have a burning question you don't get to ask today, my email is molly@vims.edu, and feel free to contact me. Thank you.
Scott, is it working? And then you can go and then go back to this one. Yeah. And then click yours. Okay, so I'm the last speaker, and we want to make it short to have some time for questions. And so we know there's a lot of pressure for water supplies in Eastern Virginia, and we have a lot of problems with groundwater, of course, sea level rise, stormwater. And basically, my talk is about this lower alternative water supplies, which I list 3: desalination of seawater and brackish water, and rainwater, stormwater capture and use, and wastewater reuse. Those are the 3 alternative water sources that we could have in the area. So I just want to make this brief. This was the 3rd option. Wastewater reuse is getting very common. And there's a Water Reuse Foundation working on this, and California is really getting popular, in Nevada, Las Vegas, and this slide shows in Beijing, China, which is a highly populated area, a lot of hotels have a water treatment system in the basement that they treat the water and recycle it inside the hotels. Basically, so the 3 uses of wastewater I listed here is in-building recovery and use, as this is in Beijing, agricultural use after some treatment, and groundwater recharge. And groundwater recharge of wastewater, treated wastewater, has happening for a long time. It's very common in Israel, And also, many years ago when I studied groundwater in Long Island, New York, the wastewater has recharged between the fresh water and salt water to prevent the salt water coming in. So they call it actually a water curtain. So, but it's still in Eastern Virginia, it will be probably some time we come to this option. So desalination is the other option, removing salts from brackish water and seawater to produce potable water. And the major criteria for this is total dissolved solids, which we say as TDS. And a TDS could have between 50 and 60 elements or ions in it, but most common like calcium, magnesium, sodium, these are the most common ones. So brackish water has got a TDS of over 500 milligram per liter to up to 30,000, that's the definition. And saline water or seawater, mostly 30,000 to 50,000. So Chesapeake Bay itself is probably in that range. And brine water is the more concentrated salt water, which is produced after the salt is removed from fresh water. Of course, there's a salt production that's called brine water or concentrate. So Desalination Technologies in the US, reverse osmosis has been developed since 1960s. So more advanced versions of reverse osmosis coming into stage right now. So in the US, it's very popular. One advantage of reverse osmosis is also you can treat wastewater with reverse osmosis. And basically, this is the way how it works. There's a membrane that pressure is applied, and the salt water is moving through the membrane. And the freshwater molecule passes, and the salt remains. And that's called rejected salt or concentrate or brine, which will be higher concentration. And this has to be disposed of. So this is a big in field of water treatment is a big area of technology and research. So some of the problems with the desalination is they're energy intensive because you use pressure. When you use pressure, you use electricity to move the water through the membrane. And also disposal of the concentrated brine takes energy. Membrane fouling or biological fouling mostly is a problem. And reject salt or concentrate management is a problem. And regulation and permitting is, in a lot of places, there are no direct regulation permitting, so you rely on some other laws of drinking water and waste disposal and other things to take care of regulation. I'm going a little fast, but in Eastern Virginia, actually, as it was mentioned, the saltwater intrusion, or maybe even some of it's natural. We have coastal aquifers, we have salt in it. They're brackish coastal aquifers, which the salt concentration could be over 500 to several thousand, 10,000 milligrams per liter. So so it's got a potential in Virginia in terms of water supply. So here, as I said, it's energy intensive. In Virginia, it's all fossil fuel-based desalination. And these are some of the plants. This is an older slides, which place I visited sometimes back, but these are some of the desalination plants for in coastal and in the area, in Hampton Road areas, in these places that we use brackish water for water supply. So already exist in Virginia. In North Carolina, also in Cape Hatteras areas, in these places, there are brackish groundwater is used. But major desalination projects right now are in California. The largest, probably in the United States, I think, is in California now. Also, we have desalination, which uses, seawater. Also, we have it in Florida and Texas. And these are, in the future, these are the potential areas that, of course, we could use salt or brackish water if we need more water supplies in Eastern Virginia. So as I said, these systems are energy intensive, so that's what we call water energy nexus, the relationship between water and energy. About over 4% of the energy resource energy in the United States, between 4 and 5% is used in water sector. in water supplies and wastewater. So 5% energy use is a lot of energy in the United States. So energy efficiency or energy conservation in terms of water supplies is really important. And also there's the potential now for integrating renewable energy and water infrastructure in coastal Virginia. This is not Virginia, but in the Middle East, like they use a lot of solar energy for desalination of water. In other countries, like here, I have a couple of examples in Australia and in Germany, they use wind power to generate electricity and use it for desalination. In the recent news, the offshore wind energy in Virginia is going to be a major project probably happening. So desalination plants in Eastern Virginia probably in the future could move to use electricity which is produced by wind. So that's something we're looking into future. So in terms of other source of water, so I mentioned here stormwater. There are two types of stormwater collection systems. One is rooftop rainwater capture, and the other one is a stormwater runoff from paved areas. And so that's the way it happens. In the US, about 10 trillion gallons a year of untreated stormwater runs off from roofs, roads, and parking lots. And of course, it's happening in Virginia too. And well, I call the stormwater runoff a wasted water because we don't use it. In case of Eastern Virginia, it goes to Elizabeth River. What's the other river? These rivers which are in Hampton Road area, they collect the waste, the stormwater runoff, and it goes to the bay, actually. So it's not only waste of water. The stormwater from paved areas includes all these contaminants, which are ending up in rivers and in the Chesapeake Bay. So control of stormwater runoff is a critical issue. So as long as we control it, so this is a futuristic thing, we should thinking about harvesting the stormwater runoff for potential uses. So in terms of potable water, in urban areas, about 2/3 of high quality water, which is energy intensive, is used for non-potable uses. Like if a family in Northern Virginia is using 500 gallons of water, from that 500 gallon, only 100 gallons is used for drinking and washing and that sort of thing. And 400 gallons is used for car washing and lawn gardening, lawn watering and that sort of thing. We don't have to use actually energy intensive water for those purposes. So rainwater could be, if it's captured, could be a substitute for that use. And 1,000 square feet of rooftop captures about 620 gallons of water for 1 inch of rainwater. So in Virginia, the average rainfall per year depends on the locality between 43 to 46 inches per year. So you multiply that for 1,000 square feet, you can know that from one small building, you can capture a lot of water. If it's a commercial building, you can catch much more water. So the other thing which is important to know, rooftop areas constitute about 30 to 40% of impervious areas in cities. So if we capture the rainwater from rooftops, so we can use it for non-potable uses indoor. With treatment, there are places we can use it for potable purposes too, because drinking water treatment is advanced now. But most common is now non-potable use, like flushing toilets and that sort of thing, and also for cooling. Outdoor uses, lawn irrigation, car wash, and gardening, and other uses in urban agriculture, community gardens, and in groundwater recharge. We did see that a lot of the stormwater runoff is wasted, and a lot of rooftop rainwater is wasted, so because it goes to the gutter. So if we collect that in the areas that the Scott needs water, so we can recharge the groundwater with the stormwater actually, which is happening in some places now. So benefits of rainwater harvesting provides alternative water supply source, effective method for stormwater management, and facilitates water resource conservation and energy conservation as a decentralized system. So in potable water system, we use the energy in 3 places. One, water source development, like you pump the water from river or from groundwater. Then the second time we use energies for water treatment, like if you use reverse osmosis or other methods. And the third one, which is more energy intensive, is pumping the water to storage tanks, which is for distribution, to keep a high pressure in the faucet. So distribution usually uses about 2/3 of energy, and water treatment about 1/3, depending on geography. So I give some, this is like a vision here for Hampton Roads. If you see the last slide here, and I use some of the reports from Hampton Roads that you see the acre areas, impervious area in Hampton Roads in the last part of the column. I also did calculation for Newport News and Norfolk and Virginia Beach. But then if you look at the Hampton Roads, which includes all the areas in the Chesapeake Bay, not all the areas. Well, this table shows the areas which are within the Chesapeake Bay drainage area. Parts of Hampton Roads are not draining into Chesapeake Bay, but a large part of it's draining in Chesapeake Bay. So that's the amount of water which is produced by runoff from pervious areas in Hampton Roads. And that's a stormwater runoff in millions of gallons, which goes to the rivers and eventually goes to Chesapeake Bay. So I call them wasted waters. And in this, again, if I use that stormwater runoff, the total urban stormwater runoff, and I assume that 30% of that is coming from rooftops. So the right column shows in Hampton Roads and other cities how much million gallons of waters are produced by rooftops in Hampton Roads areas in some of the cities. So those waters, if we put them to use, so what it means, we reduce the use of conventional potable water, which is energy intensive, or we can use it for groundwater recharge. So it will be a major water conservation in the area. So as was mentioned, saltwater intrusion is a major problem, so we can recharge the groundwater. I use this term rainwater sharing cooperatives. Like a building can produce some water, but you may not use that building and that water in the same building because it may have a low population, for example. So you can use that building, that water in the next building. And also, right now, by use of geospatial technologies, actually, in 5 minutes, you can look in Google Map, and actually, you can know how much rooftops you have. You can estimate very, very fast how much water you can produce and how you are going to, if you want to like develop community gardens, you can identify available rooftops, you can estimate water amount, and you can use those for community gardens. And here's the other uses, possibly pools and also ponds. Like normally we have storage ponds for stormwater runoff, but those could be actually upgraded a little bit to have more recreational feature. In some places that's happening. And you see in the left side is urban aesthetics, that basically rainwater is used to have a waterfront or something like that. On the right side, it shows the stream water daylighting. A lot of our stormwater pipes are underground. The one which was mentioned, which Molly said does not meet the capacity. Probably open channels, open drainage systems will be coming back. It collects rainwater. Also, it could be an aesthetic value, bring aesthetic value to the site, to the location. So basically, in terms of water, energy, like in food, now we call this actually FEW. Food, energy, and water, they're very closely related. So water conservation is important for energy. Energy itself is using a lot of water. So in the food, and so we have to look at this collectively kind of to manage our water and food, have food security and manage our energy resources. So the conversation is moving to this area right now in terms of research and technology. And And these are some of the ingredients. We call it holistic approach. A major issue is public perception right now that we talked about it a few minutes ago with somebody like Wastewater. Occoquan Lab in Northern Virginia is using an advanced treat water system, treats the water and discharges the treated wastewater in the Aquifers reservoir. And downstream is taken back and treated again. It's used for drinking water. So that's a recycled water already. But a lot of our water is already impacted. All rivers which are intake of the drinking water. Somewhere in the river, there's a discharge of wastewater. So we have to get over this perception because the water treatment technologies are advanced enough to treat the water for drinking purposes, whatever you have. Otherwise, the astronauts in the space will not survive that long, you know. And the policy issues, are lagging. In terms of policy, maybe Scott can tell us more. Like it's a tedious work. Even the technology is there. It takes a long time to have a policy to do stuff. You know, that's one thing we have to work. And education, we are working on it. So I think that probably concludes my talk. So we're trying to save some time for question here. So we got about 8 minutes something. Okay, we got about 5 minutes. Yeah, but we can go to 8 minutes. So anyway, so if you have any questions for this distinguished speakers here, so please go ahead and if you have a comment or anything. And by the way, there's a groundwater session again at the museum at 1:15, which is Scott is speaker, so probably can kind of expand on what he said. And anyway, please, if you have any question, anything, if you're ready, go to lunch, because between this session, that is only 30 minutes, right? So, yes? Yes, please. Yeah, why? Scott is a regulatory person, so he will.
Does it work? All right. Okay, so you're asking about safe yield, right? Okay. There was a lot in that question. I wasn't quite sure I understood where you were going with it. And when you say they're not meeting their current capacities, help me understand what you're saying there. I would say only at a very, very preliminary level at this point. We have been in ongoing conversations for, frankly, 20 years with VDH about how to synchronize the two programs and how we look at the concept of safe yield. The Waterworks regulation has, in effect, been open since 1996. While we have had those conversations in many, many different forms, progress has been very, very slow. I'm hopeful that the current level of conversations may provide us a path forward so that we can actually move toward engaging stakeholders on a more productive dialogue about how to address the kinds of issues that you're talking about. And, you know, I think it's reasonable for that group of stakeholders to have some expectation about incentives or other kinds of inducements to, in effect, give up something that they have had for a long time. If, in fact, that's the case. I don't know that it's a given that if we were to tinker or change the current definition of safe yield, that's necessarily the end result. So, yeah, I think there's lots of preliminary conversations. I think we'll continue to have conversations probably for a number of years before we reach some satisfactory conclusion to it.
Hi, I think this is for Molly. You mentioned desalination. I was in the Middle East on a project with Virginia Tech, and the Germans have done a lot of desalination over there. One of the challenges is they end up creating more salt in the water where they're doing it, which has caused some real problems. I didn't realize we were doing it in the Northern Neck and Middle Peninsula. What's being done to address getting too much salt back in the water when we take it out?
Okay, so that's a good question. It's, there are regulations on the quantity. I don't know, one of you might be better to answer this. There are regulations on the quantity that goes back in. It is an environmental issue, changing the salinity. So there is modeling and that kind of work that's done ahead of time to help figure out what those regulations should be on how much salt goes back in. I don't know, do you want to add to that?
Yeah, I can't stray into that realm very far since it's not one of my programs, and I might be lynched by my fellow state employees. But there are, you know, as was indicated in, I think it was Tammim's presentation, a number of brackish desal plants that primarily treat groundwater. And they all have discharge permits, and they do find ways to permit them and find satisfactory treatment options that can be implemented by the permittee. So I think to some extent, you know, there may be perhaps greater fear out there among the regulated community about the ability to obtain a permit and to find a satisfactory resolution to brine management. But I think there may be more options and ability to actually get to a reasonable point than people may anticipate.
Okay, I'm in the middle of that right now. So, of course, the ocean dumping has been an option. But right now, the technology is moving towards zero liquid discharge. Basically, you're working on technologies that removes all the water from this salt water, which has got very high concentration of salt. And you produce a dry material which could be useful for other uses. So that's the way the technology is moving right now. So zero liquid discharge treatment technologies, yeah. Any other questions? If not, I think, thank you very much. It's about lunchtime, and if anything is left. So, yeah, thank you very much. Hope you enjoyed it.